The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, and good evening, everybody. Welcome to the webinar today. This is the first part of a two-part webinar series that we, NXP, and ThinkStream will be doing together. The first part, as you can see, is we'll be focusing on how you can design and deploy intelligent low-power and low-cost wireless networks. We will have time towards the end for questions, but feel free to type in questions in the question box. And we will get to them at the end of the webinar. And without further ado, I will hand it off to Gordon. Gordon, it's all yours.
Yeah, thanks, Ethan. And likewise, hi everyone. So let me jump into a couple of introductory slides. The first part of this two-part webinar series is really going to focus on, you know, the wireless edge node of the network, how to build intelligent, low-cost connected things at a low cost. So we're going to go through this agenda today in about 45 minutes and leave maybe 15 minutes at the end for questions and answers. So I'll do a quick introduction to the presenters, including myself, in a minute. Then we will talk about market trends that we see for, you know, edge node sensors and connected things between the edge and the fog. We'll talk about global connectivity, some of the challenges in how to deploy global networks that can also be low power. We'll talk about, you know, how we can then connect the edge nodes, the different options for these global networks. And then we'll talk about some device management. And we'll also at the end highlight a reference design and show a demo about how you can use, you know, the combination of NXP and ThinkStream to connect a sensor to the network. And then we'll go into a very short summary at the end, and then questions and answers. So we really appreciate your attendance. And I'm happy to be here with our partner in this webinar, ThinkStream. Like I say, this is a two-part webinar where the first part predominantly, I think, is going to focus more on the hardware and how to get things connected. And the second part of the webinar, we're going to go more deeply into how you can then, using a range of services and a management platform from ThinkStream, how you can manage the different sensor node networks around the world. And that will include how you can provision them, install them, maintain them, and then use them, use their platform to connect to different cloud services and bring more value to the sensor network that you deploy. So the three people that are presenting, I am Gordon Padkin. I work in the regional marketing team for NXP Semiconductors, focused on our microcontroller products. And I'm happy to say that our microcontrollers are part of the solution that we're going to bring you today, as they can really bring cost-efficient, low-power control elements to the edge of the network. Then we also have Neil Hamilton. He's the VP of Business Development at ThinkStream. And we've got Bruce Jackson, who is the Chief Technology Officer at ThinkStream as well, on the line. And they'll be doing most of the presenting today to go through the solution that has been developed.
Hello, good afternoon.
Yeah. So just very quickly up front, I want to set the scene. I mean, NXP is a semiconductor supplier. Our objective is really to deliver secure connections for a smarter world at the top level. Now, what does that realistically mean, and what's the context of that into the webinar that we are bringing you today? Well, if we look at the total picture of the solution that NXP brings, we can bring the entire solution from the very edge of a smart network. And that means that we can bring microcontrollers, microprocessors, NFC, RFID, sensor and analog technologies, as well as connectivity technologies that allow people to develop and build smart, low-cost sensor networks. As I said, we do provide some of the connectivity bridges that allow people to then connect up to the gateway, where again we can bring a range of scalable solutions, and we bring as well solutions that can operate in the cloud and that can do big data processing. But the focus of this webinar series is really about how we take edge nodes and get them connected into the cloud seamlessly over a low power, long range network. And let me move on to the next slide. So if we look at what we're going to cover today, if you imagine in the world of the Internet of Things, or the next wave of Internet of Things enabled products, there are a whole range of things that can benefit from being connected. And any of those things, if you think about very simple sensors, could use an NXP microcontroller or microprocessor. And then, of course, you need some connectivity block, some hardware block, to then connect that piece of hardware to the network. But also what is critically important is the software enablement that runs on top of the hardware to then build that connectivity bridge, and that's where we will spend some time as well. So if you look at what components NXP and ThingStream bring, NXP of course brings its hardware, then it brings the NXP MCU Expresso software development kit, which provides us a way. It's got your RTOS, your low-level drivers, your APIs, and your middleware to build out a rich application. And then on top of that, we have the ThingStream connectivity software block that will then allow you seamless cloud connectivity. And once you have the hardware components, the software components in place, that means that you can start to leverage cloud infrastructure, which can bring you provisioning, machine learning, additional storage, all of these things that can really add value to your end customers and the sensor networks that you deploy. So without further ado, I want to hand over to Bruce and Neil at this point to do the next part of the introductions.
Very good, thank you, Gordon. So it's Neil here. Hi, everybody. Thanks for joining. So I was going to provide a bit of scene setting before we move on to Bruce demonstrating and showing you the technology in action. And really the opening part here is very much around talking about the opportunity. I love showing people this Beecham research slide, which you don't need to necessarily look at the details. What it's really telling us is that every vertical industry is adopting IoT in some shape or form, which is just creating huge opportunity. But what it's also doing, it's giving us a challenge of how do we connect billions of devices to our back-end applications and solutions that companies are deploying globally. And what's also interesting is very much, in the topic of this kind of webinar, is very much the fact that the majority of these devices are going to be deployed to the field. They will need to connect wirelessly, infrequently or frequently, will need to live on battery power for 3, 5, maybe 10 years plus. And most interestingly, they really will only be communicating bytes of data. They're not going to be high bandwidth consuming devices. And this is why this particular webinar on this subject of low power, low cost, and efficient communications between devices and back-end applications is becoming more and more prevalent, and more people want to see what types of solutions there are in the markets. Now, one of the reasons we believe, in our experience so far with customers and partners, is why these devices are becoming, well, while they're communicating only bytes, sometimes obviously it's because it's for very simplistic, condition monitoring information, but it can often be more complex data. But partly it's because a lot of the devices in time will be making more of the decisions out on the edge themselves. And there's a number of benefits for doing that. And this is hence why we're going to show you some of the technology and how you can deploy and manage these types of devices effectively. And the real benefits here are predominantly for speed. So decision making can be milliseconds, maybe in critical situations for different types of applications, as opposed to seconds or longer when there's a round robin back to applications in the cloud and back out to devices again. So some clear application benefits. More importantly, we'll see there's cost benefits in terms of there's less data. If you can get the device to do more of the decision making, then there's less use of an actual communications network and less to pay in terms of the actual the data costs involved, or the cost of transporting and communicating. And the other area is very much around, if you're not sending so much information back to the cloud, there's less compute happening. So we're saving energy and again, further reducing costs in our end solutions. So there's some real benefits all around from the application standpoint, right through to obviously the pure efficiencies in the cost of these solutions. And as they go down in terms of overall costs, then the return on investment is going to be better, and we're going to see an acceleration in these deployments of such solutions. So when at ThingStream we look at the DNA, if you like, the breakdown of a smart thing or an intelligent device, we think there's 5 real important factors that have to be considered, and no doubt you guys are taking a look at such things. One is very much around the connectivity, and we'll come on to that in a moment, but typically a device should be be able to be deployed and simply just work, removing the challenges around the connectivity involved. We also see that programmable control is important. Examples being, if you have a product that has a geofence and when it wakes up, it works out it's outside of a geofence, then it needs to do something. And so being able to maybe wake it up more frequently or get it to then communicate back to an application is important, but you might want to change those rules during the time these devices are deployed in the field. And that's really important. You don't want to be necessarily recalling devices or sending engineers or service staff out to the edge and effectively swapping out or flashing devices and things like this. So having some element of control over these devices is really important. Low power is obvious. We don't want to be, again, recalling or any of that kind of stuff from a power perspective. Security we see being increasingly naturally more important, very much where, again, engineering or industrial equipment, you don't necessarily want to even expose an IP address, and this is one of the benefits of using the ThingStream connectivity solution, is very much around that. And low cost, it comes as part of the packages we see from the vendors in the industry. That's what everyone's bringing to market, are these things that are enabling us to build lower cost devices, connect at a lower cost, and run whole applications much cheaper than we can or have done before. So if we just focus for a moment on just ubiquity and a simple kind of use case, just to give you some context, there's a lot of discussions around different types of radio networks and what should be used, and we're just focusing on maybe some of the more popular ones. But a typical use case that we find that we work with is here, for example. If you have a customer who have maybe heavy plant machinery and they want to maybe track the conditions of it, or certainly its location, just for security and maybe some predictive maintenance capabilities. Often some of those solutions need to run, again, off batteries because they don't want to be associated with the power on board. You really, as a business, you really want to choose a single solution and confidently deploy that in your device, in your machines, and then just deploy them across your geographies. And let's assume that is just, for argument's sake, a European geography. Well, I need to think about my connectivity as a decision maker in that business. And if I look at the options today, such as Sigfox and LoRa, well, I don't want to limit my business footprint to just where these current deployments are for these particular technologies. I don't want to be hindered. I want to be able to confidently just do business anywhere in Europe, wherever I wish. So that then leads us maybe to some other options in the cellular world. Obviously, with the developments of the MB technologies, which again currently are they're some in trial mode, some in early deployments in just cities. And again, if I've got an example like a forklift truck I'm showing you here, that could be moved across the border. It could move to a rural area. There's again no guarantee that we're going to have the coverage of the new types of cellular low power options. So this is where ThingStream comes in. We very much have a unique proposition that we'll come on to explain more, and Bruce will go into more detail. But effectively, what we've done is we've looked at the DNA of an IoT solution, and we've actually built some technology, built some products ourselves to really understand the challenges in this market. And so the ThingStream proposition is comprised of 3 key components. We've seen that from a programmable point of view and the control point of view, and again for the low cost, MQTT is an extremely efficient protocol for using for IoT. So we've taken that further. We've actually built a global MVNO, which effectively enables devices to use our SIM cards and communicate using MQTT or a variant of MQTT from pretty much anywhere in the world. That brings benefits of being low power. We're actually using we're not using cellular data. It's a lower level channel within the cellular networks themselves, and we think this is pretty exciting. And we're starting to unblock some of these, connectivity challenges, not just the ubiquity, but also the intelligence that's required and the programmability as well. Naturally, that comes with that. If you're working with MQTT, you're going to need a scalable, carrier grade broker, which can support the overall communications between these billions of devices and your back-end applications or your customers' applications. And the final part, which we're going to go cover in the second webinar more, but it's very much around having the ability to control and design clever application flows and design applications around how you might want to transform the data itself into different protocols and communicate with different systems, but all from a very easy to use programmable interface. And as I say, in the next webinar, we'll cover more of that. So at this point, I'd like to hand over to Bruce, who can explain more about how we've gone about working with these technologies and show you some real technology in action.
Thanks, Neil. Before I move on to talk a bit about the platform, I just want to point out this photograph you're looking at here on screen. This is actually one of our reference designs that we produced, and I've actually, in part of the demonstration where we're going to get out the MCU Espresso tools and actually write some code, this is basically the target device I'm going to use. You can pick these up online on our web store. Comprises an NXP LPC824 processor, along with communication modules, GPS, all in a handy button-sized form factor device, along with a battery. So I'm just going to remind you of that because that's what we're actually going to be working with a bit later on in the presentation. So let me tell you a little bit about the ThingStream architecture. As Neil mentioned, ThingStream is essentially, you can think of it as being an MQTT-based overlay network that uses some elements of 2G, 3G, and LTE cellular communication that aren't typically used by people. Our business has a background in supplying infrastructure to mobile network operators, and we believe that was a very good fit. A protocol called USSD, Unstructured Supplementary Service Data, was a really good fit for certain IoT applications. You can think of it very much, USSD, as being similar to SMS, voice, and then the different flavors of data. So it's a fundamental service that makes up 2G and 3G networks, and then it is an overlay service on top of LTE, and I can talk more about that later. And essentially, USSD in itself is not super friendly to use, so we have wrapped it in a MQTT wrapper to make it easier to use both on devices and on the server side. So what you end up with is effectively a cellular overlay network that works across 190 countries and provides you a ubiquitous communication channel that is the same, both in terms of cost and same in terms of availability and ubiquity anywhere on the planet. Now, in the two webinars we're doing here, in the second webinar, I'm going to talk a little bit more about the actual platform that runs behind this, but today is much more of a sort of hands-on engineering focus on the device side of things. So in this diagram I'm showing you here, although this is the total architecture of the ThingStream platform, we're going to be talking about stuff on the left-hand side, and in particular down here in the devices section in the bottom left-hand corner, those devices and the SDK we provide to manufacturers and to developers that allows you to use the ThingStream platform. So that's the focus of today. So if I step on to here, I'm going to talk a little bit about MQTT. Many of you may use MQTT, many of you may have heard of MQTT, but just a little explanation of what it's all about. So first of all, MQTT is a message-oriented protocol. It allows you to create messages that you can send from devices to enterprise systems and the other way around. It's a bidirectional protocol. You can put any type of payload in those messages. They're not restricted to a particular type. And importantly, you don't send messages from one thing to another. You basically have it's a publish and subscribe model where you create topics which can be structured in a hierarchy, but they can represent anything that makes sense to you. And you essentially send a message to a topic. Then another device or your enterprise system can subscribe to that topic, And that will mean that when a device publishes something to a topic, anyone who's subscribing to that topic will get that message. Now, that has lots of advantages, but not least of all that you can have many things subscribed to a topic and many things publishing to a topic. So you can have messages that cascade through and can organize structure in terms of both the application and how you think about the application, and in terms of the management of devices in the field. So it can be extremely flexible for those type of things. We chose MQTT because it was very popular in the IoT space. It is a very efficient protocol when you look at the bytes over the wire compared with something like HTTP. And in fact, we use a variant of it called MQTT-SN. The SN stands for Sensor Network, and it was originally designed or thought about for typically low power sensor networks. So things like Zigbee devices, where you want to reduce the payload, message payloads even further perhaps because of bandwidth constraints. But actually it fits really well then with using this over a cellular network to optimize the amount of data that you end up sending across the air. So that's what we're using. So that's if I now move on. Now, the normal MQTT lifecycle is pretty straightforward. An MQTT device would connect to what's known as an MQTT broker. So that's the thing that manages all of that structure of topics. And then we'll do one of three things. It can either publish data to a topic, it can subscribe to a topic, or it can basically just ping the server to say that it's alive. Now, some of that's quite important to maintain the life cycle of things. So for example, if a device connects and says, I'm going to be here for, say, 60 minutes, as long as it comes back and pings within the 60-minute period, the server will consider that the device is there and is connected. In effect, it maintains a state in that regard. And then at the end of a session, obviously a device is expected to disconnect to say that it's gone and is no longer contactable. Now, MQTT-SN adds some additional lifecycle components that are really useful when thinking about building disconnected and low power devices. So this is the chart here is similar in the center. If you start in this connect box on the left-hand side, you've got the same connect followed by publish, subscribe, and ping. But there's another option up here that's called register. Now, register, in order to optimize bytes, you might think, when you think about topics are usually referred to in MQTT by long names. So if you remember the example a couple of slides back, you might have a topic name like devices, North America, customer A, for instance. And so that's quite a long string. Every time you send a message, if you have to specify that great big long string, you're right there wasting 100 bytes of data just to send the name of the topic. So the register component in MQTT-SN allows you to basically create a 16-bit alias against the topic name. So you can compress that whole 100 bytes of the topic name down into a 16-bit ID that you can use. And that can be done both in our system on the server. You can create a pre-registered topic where you just basically take a topic you've created and create an alias for it, or you can do it programmatically from the client. You can call this register operation that performs that same function. Then if we go back to the connect, there's another thing that you can do that's interesting to do with lifecycle. So straight after doing a connect, you can do a disconnect and specify a timeout. And what that basically does is allows you then to go to sleep for that timeout period. And the server will collect any outbound messages that are targeted to this device or that this device is subscribed to, and will hold them on behalf of that client, provided that client comes back and pings within that timeout period. Now, during that disconnect, you can go to sleep, you can turn the power off, you can shut down, go into low power modes, deep sleep modes, that kind of thing. Safe in the knowledge that any messages that are targeted for your device, you'll still get. As soon as you wake up and ping the server, any outbound messages will be delivered to you by the server on the back of that ping request. So you can then collect them, and then you can go back through the formal cycle of a connect and do all of that stuff, or you can just disconnect again with timeout. So you've got a number of options there that allow you to maintain and manage the life cycle on a battery-powered device and still make sure you don't miss messages that are targeted for you. As one final thing that you can do with this, normally this cycle of connect and then publish to a device obviously requires you to go through a connect cycle. MQTT-SN also allows you to do a publish with a particular quality of service. I should have mentioned that. MQTT also supports a number of different quality of service metrics. All the way from an MQTT-SN specific one, which is basically fire and forget. So I send a message and I have no idea whether anyone got it or not, through to quality of service levels where you can assure that a receiver has received it. They will only ever have received one copy, and you know they got it. So there's a whole range of different quality of service, which is another thing that makes MQTT popular, because it allows tailoring of that to fit the application. But MQTT SN has this option of a fire and forget without the connect. And in fact, I'll show that in the demonstration I'm going to be doing in a minute. So to talk a little bit about what we provide on the client side of this, we have a client SDK that looks structurally as per the chart here on the left-hand side. So starting from the top and going down, we have a client API that corresponds to basically MQTT, or in our case, MQTT-SN. It looks a lot like an MQTT client that you may have seen that you can find out on the web. It certainly represents the standard MQTT operations: publish, subscribe, connect, etc., but adds the ones for MQTT-SN as well. Now, on top of that, we have a set of platform-independent code, which we provide in a binary, and that is portable across a number of platforms. Obviously, most of our customers are using ARM-based designs, and so that's the typical way we would supply that. We then have two other APIs that are of interest. There's the modem transport and then the serial transport. And these allow our customers basically to create customizations on top of our SDK. Now, starting at the top, if you wish to integrate at the modem transport level, essentially what you're saying is that the modem that you have underneath, the cellular modem that you're using underneath the modem transport API, is essentially a modem that's compatible with 3GPP 27.007. Now, that's a specification that you may not be familiar with, but essentially it is an extension of the regular Hayes modems. So it's a bunch of AT commands that have specific functions for operating in cellular networks according to the 3GPP spec. So, for example, the largest manufacturers of cellular modems, and I can think of, for example, Telit, Simcom, Gemalto, U-Blox, Quectel, Sierra Wireless, all use that same common code base. So they also provide modems for 2G, 3G, and LTE that are all compatible with 27007. So if you're picking a device from one of those guys, chances are it will work with our modem transport. There won't need to be any changes there. Which takes us to the next part, which is the serial transport. Now, clearly, in the case of the serial transport, when you design your own hardware, it almost certainly isn't going to look exactly like our hardware. And the serial transport gives you the ability to provide your own implementation below that does the stuff like decides which UART you're going to use, sets up the UART properties, parameters, sets up any power kind of considerations you've got to think about, all of that stuff. So that's the real low-level implementation. Now, in our SDK, we provide a few reference implementations of that. We've ported it to a range of platforms, from Linux all the way through to things like the LPC 824, which we're going to show today, which uses the obviously the NXP API and toolkit to deliver that solution. So it's pretty portable across a whole range of platforms. So let me now take you to actually show you what I'm going to be using here. So for the demonstration, I'm going to be using, I've got an LPC Link 2 card here, an NXP LPC Link, which essentially gives me a JTAG interface onto one of our ThingStream buttons. So that's what you can see right there. This obviously has a Simcom modem on, has GPS, it has an NXP LPC 824 processor, and I'm going to be also using NXP MCU Espresso version 10 for the development. So if you just bear with me 1 second, I'm going to come out of the presentation and share my desktop with you all. So let's move this out of the way. Hopefully you can all still see this. What I'm now going to do is run up MCU Espresso. And for the purposes of this, I'm going to create a brand new workspace. So I'm going to go up into here, create a new folder for this, which I'll call NXP. So we've got a brand new clean workspace. So this is going to be basically what happens when you try this yourself. If you download the MCU Espresso toolset and get our SDK, this is what you're going to see out of the box. So I'm just say OK to that. This will start up. Okay, so the next thing I want to show you is the ThingStream website. So within the ThingStream website, at thingstream.io, when you have an account on here, you can create an account. Just go to the thingstream.io website, and you can register, create an account. There is a section in here called Downloads, and from the Downloads section, you can see a number of downloads that we make available to you for various purposes. And in particular, you can see the SDK there. The top two options are the SDK for starter kits and modules, which we supply, and then the SDK for buttons. Both of those are based on NXP processors. The starter kits and modules are KL27256s, I think, and the buttons are LPC824s. So that's where you get the SDK from. It's simply click in there and download it. Once you get that, let me run through what you do. So the first thing you can do here is we can go into File, Open Projects and File System, and then I can find, I've put that on my desktop. Oh, sorry, my desktop, which is here. And I'm going to select the SDK. Once you unzip it, this is what you'll get. And it opens up to 3 projects that we can now import into the MC Espresso environment. So one of these projects is purely a documentation project, and I'll show you some of that. And there are 2 other projects. One which just exercises and does essentially all of the operations that you would expect to find in the MQTT lifecycle. And the second application, which is effectively a prototype of a tracker. So I'm going to close this down because we don't need it. And I'm going to open up the tracker application. Now, the first thing I'm going to do here before I do anything else is just to clean the workspace up, make sure everything's clean and the projects are all clean. So we're good to go. I'm now going to just run this one up. So when you import these projects, they come with a number of different build configurations that you can use for different purposes. I want to build a debug build, but I can also put in make a release build if I want to build something as a binary, which I'm going to flash onto a device. But in this case, debug is good, and so I'm going to debug this application right here. Now, while this is starting up and doing its thing and transferring the information, what I'm going to do is show you, and we'll see this when it's ready to go, I'm going to show you the documentation in here. So I mentioned that the document, this is, if you look in this window here, you can see the structure of the ThingStream SDK and the different areas at which you can actually place code yourself. But the normal ones are here at the serial port driver, here at the modem transport, and then from an application standpoint, the client API is what you'll be using. So if we take a quick look at that, you can see in here, this is really the functions that ThingStream provides you. So create an MQTT client in effect, destroy it, connect it to a server, disconnect it, check to see whether it's connected. Now that is connected operation actually performs the MQTT ping operation. It tells you whether you're connected, but it also does a ping at the same time. The register operation is what we described when we were talking about MQTT-SN specific things. So this allows you to associate a topic name and to get you a topic alias back. Publishes data. Set subscribe callback basically allows you to take a topic, subscribe to it, and this function will be called back. Oh, there we go. So we'll come to that in a second. I'm just gonna, sorry, I'll go back to the API. That's ready to go. So I'll carry on talking through here. So the function you provide here will be called back when a message arrives that is targeted from your device. So ThingStream is bidirectional. You can send and receive messages at any time. So if you're subscribing to a topic, the callback function as well get called when a message arrives for you. You can also subscribe to topics by their name or their topic type. So there's different options for that. Subscribe name, if you really want to use long names, you can. And then you can obviously unsubscribe. Now, client run is an unusual function, essentially because the platform doesn't assume that you'll be running on a device or an operating system that supports threading. Client run essentially allows you to check the contents of the buffer. So the ThingStream SDK retains a small buffer internally, which it uses for reading data, typically off your interrupt driver from the UARTs, and it puts it into a buffer. So intermittently, you call the client run method just to see whether there is data available for you and whether there's anything you need to do with it. And at that point, essentially the callback will be called if there is data come in for a subscribe, etc. So that's how the SDK functions. So as you can see, the API is pretty simple. So as you saw in the background there, that started running. So it's in debug mode. So if I close this out here and we actually look at, this is the main method of our application. You can see in here, it starts off with some pretty normal stuff. So it initializes the platform, does some chip IO. We've got some LEDs on these devices. And obviously we also have this function set up GSM pins. That's actually controlling the UART function, so it's setting up the pins and controls that are being used to control that SIMCOM cellular modem. A number of other things in here dealing with power and charge status pins and charge status LEDs, etc. All the kind of initialization stuff you'd expect. Now, if I hit go and start this running, you'll see the debugger starts to do its thing. We'll get some output on screen here. So you'll get some output for us, and the first thing you see is it says it's waiting for a button press, which is typical. So effectively, that's what the device does. It sits and waits for me to press the button. Now, if I carefully reach over, you can't see this fortunately, but if I carefully reach over and without hopefully interrupting the JTAG, if I press that, hopefully there you go. So we've got a button press in. I've now got some flashing lights, and you can see you're getting LEDs flash. You can see all the stuff appearing in the debug sequence as we're actually doing our thing. Now, separately from this, I'll just show you something else. I have an application here called MQTT Box, which is a simple Chrome plugin that allows you to access MQTT. In effect, I'm the enterprise from within this. So I mean, this is a real MQTT client connected to our platform. So if I go in here, I can do stuff like publish data, and I can also subscribe. So in this particular case, I'm going to subscribe to this topic, and I'm going to move that out of the way. And you can see here in the debug sequence down here that our device has done its thing. What it's done, the application does something really simple. It first of all does a cell survey to produce information about all the cell sites it can see, and also the strengths of those, which you can use for triangulation purposes. The ThingStream server platform allows you to basically take that data and convert it to a position. It also fetches GPS data if it can, which since we're inside in a room, I don't think we're going to get any GPS data, but we'll see. So that's on the publish application. If I go back to MQTT Box, you can see on the right-hand side, there is the data in question. So it's got a bunch of data that we picked up from the device, whether the button was pressed, whether it was a long press, how did we get a GSM location. So you can see in here, this data here, this MCC and MNC and signal strength and cell ID, LAC and LAC. Basically, that's the data for each cell tower this particular device can see. So there's a whole range of them right now. Any of you who know your stuff will know that from seeing the MCC that we're in Switzerland today, and so that's the data that you pick out from all of these type of things. You also get some additional MQTT information down here, but that was basically me sending a JSON payload across the air from our button to our server platform. So that's all good. You can see what the application does. Essentially, I press the button, it gets the GPS data, gets the cell tower data, sends it across the air as a JSON payload. Simple application. But it's not really a tracker, it's more kind of a one-off position location when I press the button. So what we're going to do now is modify this to turn it into something that's more like a tracker. Now, there are a couple of places in the code. Oh, actually, before I talked about changing it, what I wanted to show you is where the real meat of this happens, so you can see how simple it is to use the SDK. So I'm going to, sorry. So this is actually the function that sends messages. Hopefully you can all see this. The information being passed into this is essentially some data about the type of the button press. You saw that in the JSON payload, it came up telling us whether it was a long press, etc., and what time that happened, and then a pointer to a transport structure. The transport structure is essentially the very low-level representation of the serial transport. So that's the kind of the wrapper around the UART ultimately in the system. So that's the part that you would effectively create your own implementation for, typically using our code that we provide as a basis for that. So that's essentially, you can think of that as being a wrapper around the UART. So this does something, it's pretty simple to see exactly what's happening right here. We're creating a ThingStream transport around that. And then down here, we can create a wrapper around it for logging purposes. So all of this stuff is just creating the ability to log that output. So the stuff you saw down here, particularly where these lines here, this is simply the logging function that we have wrapped around it, so it's easier to debug what's happening. But the procedure is really straightforward. There's the client create that creates ourselves a new ThingStream client. That's where we set the callback to say if data arrives at the button, if we're sending data out from the enterprise to a button or to the SDK, that's the callback function, subscribe callback, that's going to get called. In this case, we're doing, the next thing we do here is a client publish. So you can see there's the quality of service, MQTT-SN_QoS-1. So that says fire and forget. We're sending it out to a topic, and that really is all you need to do. So that's for simple fire and forget. That's it. There's nothing more to that. So it's really about 4 lines of code to get started and start sending data. And that's including the ability to set a callback to receive data on the other end. So it is really very simple from an SDK point of view. I'm very familiar if you're used to using other MQTT clients, what you have to do here. But obviously we're doing this on a microcontroller which has only got 32K of flash and 8K of RAM. So this is, and I should point out, we don't use all of that by any stretch of the imagination for the SDK. So let me just now go and make some modifications to turn this into something that's a bit more like a tracker. So what I'm going to do is, so the first thing I want to do here, I know from obviously because I know how the app was written, that this started by the button press. The button as a piece of hardware is an interesting design. Essentially, you can see there is this function here, hold power on. The button is essentially off until you press the button. It has essentially a power latch in it. When you press the button, there is a capacitor that charges, and when you press the button, the capacitor discharges and provides enough current for the microcontroller to boot and stay alive for around about 200 milliseconds. So the hold power on actually configures a GPIO pin that then keeps the processor power switched on. So you have to do that within the first 100 milliseconds to be safe of the processor boot to keep the power latched on. Now, in our case, because what we want it to do is to effectively, once we press the button once, we want it to carry on running in a loop. We want to fix this so that it will not go back off again, because as usual, normally what happens in this application is when it's done its fire once, it'll turn itself back off again. So we're just going to cheat and stick this in, hard code this to be true. So that's the first change we want to make here. The second change we want to make down here is we use, actually, we have in this file here, mvmem.c, we actually use some of the flash to retain state about whether the button should operate in tracker mode, and also we allow you to send messages in this test application, this demo tracking application, send a message back to the device to say how long you want it to be between pings. So how often do you want it to send that data? By default, this value, mvmem pointer auto mode minutes is greater than 0, is set to 0. So it's an area on flash that's normally set to 0. And what we're doing here is checking to see whether it's got a different value. Now, if that is set to 0, which is its default, once it's run once, it'll go back to sleep again. So we need to change this just so that it will always keep running. So I am going to properly hack this by just sticking in a true right here and then commenting out the rest of the line. So this is now going to assume that this is set to a non-zero value. And so it's just going to cycle around. And by default, this will be set to a minute. But you can, as I say, this application, part of its purpose is you can send a message to a topic that the button is subscribed to. And when it receives that message, if it's of the appropriate type, it parses the message. If it's the appropriate type, it'll set this area on MVRAM such that you can configure and change the time between each location data update. So now we've done that, we can just build the project again. And then we can debug it as we did before. So that's starting up again. What I'm going to just quickly do is go back to MQTT box. I'm going to close that down and I'll subscribe to it again just so it clears out the information that we have in there. The portal itself, the ThingStream portal, allows you to do some other things with regards to devices. You've got ability to actually look at the status of the item of the devices you've got. I think this is probably the one that we've been using for this. And I can see a bunch of information about the activity status of this, and I can even look at the low-level traffic logs if I really want to. It can be useful when you're doing a hardware development to actually see what data is actually going over the air, etc. But you have ability to see some of this stuff from within the ThingStream portal, the server view of your devices and how they're performing, when they were last seen, when they were last connected, etc. So we're just waiting for this application to start to transfer onto the button and start running. I'll just quickly, while we're waiting for that to come up, I'll show you an example of, for example, the modem transport code. So this is an area where you may need in some cases, if you're using a non-standard modem. Oh, we're actually starting going now. Sorry. So let's just kick that off, and you can see what's going to happen. So this is going to do the same thing as before, but it's not going to wait for a button press, and it's going to keep looping around. Every time it's run, it's going to go to sleep for a minute, and then it's going to come back down again and rerun. So just so you can see what typically you have to implement if you're implementing your own modem transport, you can see here some pretty straightforward things. It's setting a callback function when the modems get some data back, and then essentially it's just sending out a line of data. So that at that level, the modem is simply we're expecting the modem to communicate by sending lines of data backwards and forwards to us. So it's pretty straightforward, and again, a simple interface to implement if you're building your own implementations of the modem and the low-level UART transport. We've tried to keep it something really simple. So looking back to the debug in our app now, you'll see we've now had the first publish that's just happened down there. You can see publish QoS -1. And if we go over to MQTT box, that's the first message that we've just got in from the device. Now, you might have noticed, if those of you who were eagle-eyed when I was looking at the code of what we did in the main send message method, you'll see we did our thing. Now, in this case, you'll see all of these. This has happened because, as you saw in the debug there, it says entering power down. So it's actually entered the power down state, and it's going to power back up again. It'll go off to sleep now. It'll come back up again shortly. So what we've now built is a device that it operates like a proper tracker. It boots up, it does its thing, it transmits data, it checks to see whether we have, we can configure the amount of time it goes to sleep for. Then when it comes back up, it performs the same operation over and over again. So we now have basically converted our button into something where you activate it initially by pressing the button, and now you can carry it around and it will send pings or data points from the button within every so often that's configurable by you. So you haven't got to go and return the hardware to change that. You haven't got to make software configurations. You can do that stuff over the air. One final thing just about the buttons that I'll just mention. The buttons themselves are interesting, and being able to do that and stuff and track data is interesting as well, but you can also use the buttons, and we provide some expansion in there. So some of the regular expansion and I/O that's available on the 824 is actually expanded, is actually on an expansion header on the button as well. So you can connect this to all kinds of things. You have access to an ADC, you have access to some of the other GPIO pins, etc. on here. So you can attach peripherals and sensors on this. So for example, if you want to create something that for instance, took temperature data every 10 minutes or so and sent that, you can do that kind of thing. You can build that with the buttons as a hardware prototype. For both the buttons and the modules, we provide the hardware reference designs as something that is freely available to customers to take as the basis of their other design, at least to start an implementation. So that concludes my demonstration. I think we're roughly on time, and I'm now going to pass back to you guys to Gordon to talk some more.
So let me just bring up my summary slide, folks. So just to wrap up, and then I think we can open up for questions and answers. Hopefully my slide came up okay. So what you've seen there is how to, potentially develop and deploy low-cost connected things with the cloud very easily. And I think the key value proposition, hopefully, that you got from our update here is it's, the network that the team from ThingStream has built this solution on is a truly global and secure network, leveraging the USSD technologies. And I think they're making it really easy with the ThingStream client applications, which are based on MQTT, which is really a standard in the industry. And of course, all of that's built on top of the NXP entry-level low-power microcontrollers and the MCU Expresso, which allows any developer to quickly develop applications leveraging ThingStream solutions. So at that point, I want to thank Neil and Bruce and thank everyone for attending. And I'm going to open it up with Ethan for questions that people might have on the solution. And it's also worth to note before we do that there is the attachment in the handouts, which is a presentation from today in case somebody wants to go through it and download it for more information. So at that point, Ethan, are there any questions?
Yes, there are. There are quite a few. So I'll go ahead and start. First one is, I think this is for ThingStream, but will Cradlepoint wireless modems also support the ThingStream platform?
That's a really good question, and I can't tell you that. So while we move on to a different question, I'll look that one up and come back to you. So we'll do this a bit interactively.
Okay. What is typical latency for MQTT SN messages?
The latency, so once you have a connection up and established and you're actually on a cellular network, so when you saw that in the demonstration, you have to remember the state of what we were doing there. So we were effectively, in that process you saw from once we set it going, we effectively not only turned effectively a GSM radio on, got connection to a cell site, tried to get GPS connection for 15 seconds, which in this case we didn't get because we were indoors, and then did a cell survey of all the cell sites and sent that data. I think in total that took, I don't know, probably about something in the region of about 30 seconds. If you're already connected to the cellular network and you send a message on ThingStream, you can expect that message to be sent and received at the other end in under a second. So it's relatively quick. It partly also depends on the size of the message. So individual USSD messages are basically 160 bytes in size, but that complexity is hidden from you by the SDK. So if you choose to pass in a message of 4K, for example, it will send and receive multiple messages and acknowledgements backwards and forwards between the server without you noticing it does it. You don't have to get involved in worrying about breaking up your payload packets or doing anything else of that nature. The SDK fixes all that stuff for you. So you simply deal with it. But clearly, if you're sending a data that's, say, 4K, it is going to take longer because it's going to involve multiple messages going backwards and forwards than it would do if it was a single message. So the answer is, for a single message of the type that we sent there, which was under 160 bytes, then it's substantially under a second. If you go up to, say, larger sizes, then clearly it'll take more. Now, to give you some idea of ThingStream's capacity, or the capacity of USSD, in fact, the maximum message size you can send, but we wouldn't typically recommend for an application. So the whole of the technology is basically targeted around relatively small message payloads. So I would say the hotspot is somewhere less than 4K in size, but you can send messages up to a megabyte if you wish. And if you send a message of up to a megabyte in size, then I can tell you it takes roughly a minute to send it. So that hopefully gives you some idea.
Great, thanks. So the next question is, will ThingStream work with the LPC 800 series DIP package microcontrollers?
Sorry, could you say that again?
Yeah. Will ThingStream work with the LPC 800 series DIP package microcontrollers?
Yes, it will. So there should be with the packaging of the microcontroller isn't important to us. I mean, we're obviously using one that is not a DIP package, but provided you have appropriate I/O pins to control a single UART, which is all we're actually using in this, then you're good to go. We just use one UART for this and a couple of GPIO pins, which are just essentially the on and off pin to the modem. So there's not very much being used at all.
Great, thank you.
I can just quickly answer the Cradlepoint question, and the answer is yes. Cradlepoint's modems are 27007 compatible.
Nice. Okay, and Gordon, I think this one's for you. What are the major differences between LPC 800 and Kinetis L series MCUs?
The main reason that and ThingStream used both for different configurations, the main difference between the LPC 800 is that's really focused on entry level, I would say, more simplistic applications where an 8-bit microcontroller might have traditionally been used. But the amount of resources on an LPC 800 is capped up to 64 kilobytes of memory, NVMe memory today. Whereas the reason the Kinetis L was used was because you have scalability up to 256 kilobytes of NVMe. So if you wanted to build a slightly richer, more complex sensor node, but still cared about low power, then you could use the L series. But if you cared about, cost and simplicity, the LPC 800 would be the best option.
Thanks, Gordon. So we have an attendee here who they've started to use ThingStream SDK with NXP MK64 using 3G/USSD module, and they would like to know if they can also use SDK with Ethernet connection in order to use the same platform both for USSD and I believe was it ETH Ethernet?
Yeah.
So the answer to that is yes. We have a couple of people who are doing something similar, actually. There's two ways of approaching that problem. We have one customer who has written their own modem implementation, and then based on whether they are using, in their case, they're using Wi-Fi actually, but Wi-Fi or cellular, they basically swap out the modem transport. The modem transport. So they have just implemented that API in a similar way, dealt with the hardware themselves, and they effectively changed the pointer over to the SDK as and when they require it, depending on what's connected. So that's the first approach to that. We have another customer who does something totally different. They have a rather more sophisticated hardware platform. So they're actually running a flavor of an embedded Linux. And on their system, they have taken an off-the-shelf version of the Paho C-based client. So that's the kind of reference implementation of the full MQTT platform, and they basically switch between the two. So based on something external to our platform and determining whether they were using cellular or Ethernet, they essentially swap completely the whole stack out. So they either directly talk real MQTT or they talk MQTT-SN via us, depending, and they do that externally. So it is possible, and it's just a question of choice of hardware and what you have and which approach you wish to take. Neither of them is impossible.
Thank you. And we do have a few more questions, but in the interest of time, we can take those offline. I know folks at ThingStream and then Gordon as well, we can send out these questions to you and you can reply back through email.
Very much so.
But yes,
to wrap up on, Ethan's just a reminder as well of the next webinar that's taking place on the 29th of May, where we'll focus on the cloud connectivity part and the management of the devices. So for those people that weren't aware of the second webinar, they can find the links to it under nxp.com, and they can register under our online training webinars. So I just wanted to make that point as well before we dropped off.
Yes, thank you, Gordon, for that reminder. We will have a second part to this, so for everyone who came, it'd be great to see you again there. But again, thank you all for joining, and we will see you next time.
Thank you.
Thank you very much.
Bye.
Bye-bye.